What if I told you that one single, completely invisible gas has, saved more human lives than almost any medicine in history, but also uh, was once deployed as this absolute devastating weapon of war?
I mean, you would think we were talking about some kind of weapon from a science fiction thriller or something. Like a substance so volatile it can just fundamentally alter human civilization, acting as, well, both an ultimate preserver of life and just an absolute force of destruction.
Right. But we aren't talking about science fiction here. This is entirely real. In fact, it is literally flowing through the infrastructure of your town and, likely your own home right now.
Yeah, it's everywhere.
It is element 17 on the periodic table, chlorine. And today we are going to tear apart our sources to figure out how the exact same chemical that stopped global cholera outbreaks was also somehow weaponized in the trenches of World War I.
And really the overarching theme we pull from the research today is that chemistry itself is strictly neutral. The universe just provides the building blocks and, they don't have a moral compass at all.
They just do what they do.
Exactly. They simply follow the laws of physics. So the profound impact, like the light and the dark of it, relies entirely on how humanity actually chooses to harness them.
Okay, let's unpack this because that duality is just wild to me. How does something that is capable of purifying the water you drink also act as a devastating battlefield weapon?
Right, it's a huge paradox.
So to understand that, we obviously have to start with what this stuff actually is. According to the sources, chlorine is the 17th element sitting in group 17, period 3. But hold on, for those of us who haven't, looked at a periodic table since high school chemistry, why does the neighborhood it lives in actually matter?
Well, the neighborhood is everything when it comes to elements. Group 17 is known as the halogen family. And if you look at the root of that word, halo means salt, and gen means to produce.
Oh, so they're salt formers.
Precisely. They are the salt formers. So chlorine sits in that column alongside fluorine, bromine, iodine, and astatine. And if you were to say somehow isolate pure chlorine at room temperature.
Which is hard to do, right?
Very hard, yeah. But if you did, it would exist as this dense yellowish-green gas with a profoundly irritating odor. But the reason its neighborhood matters so much is that halogens are just notoriously aggressively reactive. And the key to that aggression really comes down to one thing, which is its electrons.
Okay, I vaguely remember the basic model of an atom from school. You've got, the nucleus in the middle, and the electrons are orbiting on the outside in these shells.
Yeah, and that outer shell is the crucial part here. Chlorine has exactly 7 electrons in its outermost shell. And there's this fundamental rule of atomic stability, the octet rule, which dictates that atoms are most stable, like most content, when they have 8 electrons in that outer shell.
I get that it wants 8. That makes sense. But why does having 7 make it so aggressive? Why doesn't it just stay at 7 and, mind its own business?
Because the laws of thermodynamics literally won't allow it to. An atom with 7 valence electrons is in this state of really high energetic tension. It is so incredibly close to stability that the electromagnetic pull it exerts to grab that one final electron is just massive.
So it's desperate.
Beyond desperate. It cannot just exist peacefully. It will react rapidly with almost anything it bumps into. Metals, hydrogen, organic compounds, it doesn't matter, just to rip that final electron away.
Wow, okay. So it's less like searching the couch cushions for a missing puzzle piece and more like, I don't know, a molecular mugger.
A molecular mugger, I like that.
Yeah, it's not just looking for a spare piece floating around. It is violently ripping a piece out of its neighbor's completed puzzle and then permanently altering the neighbor's structure in the process.
Yes, exactly. And that molecular mugging is so relentless that you will almost never find chlorine existing as a pure gas out in nature. It has already mugged something else and bonded with it long, long before you ever arrive on the scene.
Which brings up a really fascinating historical problem. If it is this aggressive and always bonded to something else, how did we ever find it in the first place? I mean, it must have been completely hidden in plain sight for most of human history.
It was entirely hidden. It took a very specific kind of chemical brute force to finally expose it. The timeline kicks off in 1774 with this Swedish chemist named Carl Wilhelm Scheele.
Right, I saw his name in the sources.
Yeah, so he was experimenting in his lab, heating up hydrochloric acid and dropping in manganese dioxide. And this reaction basically forced a strange, dense, greenish gas to rise up from the mixture.
But looking at the historical notes we have, he didn't actually realize he had discovered a new element, did he? He thought he just made a new compound.
You really have to consider the era he was working in. The scientific understanding of what even constituted a fundamental element was barely in its infancy. I mean, oxygen had only just been discovered.
Oh, wow. I didn't realize it was that early.
Yeah, so Scheele mistakenly, but, very understandably, believed this greenish gas was just a complex compound that contained oxygen. He had essentially managed to isolate the mugger, but he didn't know what he was looking at.
Here's where it gets really interesting because we often have this Hollywood version of science in our heads, right?
Oh, for sure.
A scientist looks through a microscope, the music swells, they shout, Eureka, and all of human knowledge just changes overnight. But humanity sat in totally blind confusion for 36 years before anyone actually figured out what Scheele's green gas even was.
The breakthrough finally came in 1810. A brilliant British scientist, Sir Humphrey Davy, ran exhaustive tests and definitively demonstrated that the gas contained absolutely zero oxygen.
He proved it was its own thing.
Exactly. He proved it couldn't be broken down any further as a brand new fundamental chemical element, and he named it chlorine, pulling from chloros, which is the ancient Greek word for pale green.
So Davy finally puts a name to the mugger. He realizes it's this apex predator on a molecular level that just tears apart the chemical structure of almost anything it touches. Which makes me wonder, who on earth was the first person to look at that and say, you know what? We should really put this in our drinking water.
I know it sounds completely absurd when you phrase it that way,
Yeah.
but the application was born out of just sheer desperation. Before modern water treatment, drinking water was essentially a delivery system for death.
Yeah, we totally take for granted today that turning on the tap won't kill us. But historically, illnesses like cholera, typhoid fever, and dysentery, they claimed millions upon millions of lives.
It was horrific. You would draw water from a local well or a shared municipal source, and you were basically rolling the dice with your life. These waterborne pathogens were invisible, incredibly resilient, and just absolutely devastating to human populations.
Right.
But scientists eventually realized that if chlorine was so aggressively reactive, perhaps it could actually be used to attack those invisible threats.
Let's dig into the actual mechanism there for a second. How is the chlorine killing the bacteria? Is it like poisoning them?
No, it's not poisoning them the way we usually think of toxins. It is literally physically destroying them through oxidation.
Oh, okay.
When you introduce chlorine into water, it reacts to form hypochlorous acid. And when that acid encounters a bacterium, it acts exactly like that molecular mugger we talked about earlier. It viciously steals electrons from the lipids and proteins that make up the actual cell wall of the bacteria.
So it's essentially just ripping the walls of the cell apart from the outside in.
Precisely. The cellular structure loses its integrity, the cell membrane ruptures, and the pathogen simply disintegrates. It cannot survive, and even more importantly, it cannot mutate to become immune to this.
Because it's physical destruction, not a biological poison.
Exactly. Municipal water treatment facilities around the world realized they had found a silver bullet here. By adding very carefully controlled amounts of chlorine to the water supply, they could just obliterate the pathogens before the water ever even reached a home.
Wait, I have to push back here on behalf of anyone listening right now. If it is deadly enough to literally rip a cholera cell apart upon contact, why isn't it damaging the cells in my throat when I drink a glass of tap water?
That is a very fair question.
Right, like trace amounts feels like a bit of a cop-out. Does the chlorine evaporate? Is my stomach acid neutralizing it? Why am I not being oxidized from the inside out?
That is the critical question, yeah. And the answer lies entirely in the sheer difference in scale and biological complexity. A cholera bacterium is a single, isolated, highly exposed cell. It has no backup whatsoever.
Okay.
When you put trace amounts of chlorine in water, and we are talking like 1 to 3 parts per million, that is an overwhelming concentration for a microscopic single-celled organism.
But a human being is made of trillions of cells.
Exactly, trillions.
Yeah.
And our cells are part of this massive, robust, heavily protected system. By the time that water reaches your tap, the tiny amount of active chlorine left is instantly neutralized by the complex organic compounds, the proteins in the saliva in your mouth, and digestive tract.
So it gets distracted by all the other stuff.
Yeah, it reacts harmlessly with those abundant organics long before it could ever cause structural damage to your living tissues. It essentially does the dirty work out in the pipes and leaves you perfectly safe.
Which is just staggering when you think about it. The sources highlight that public health experts consider water chlorination to be one of the greatest medical and engineering achievements in human history.
Oh, without a doubt.
We essentially built this microscopic molecular fence. We put this incredibly aggressive element to work guarding our water, and it dramatically reduced outbreaks of disease throughout the entire 20th century.
And, the industrial applications didn't stop at the reservoir either. Once industries figured out how to safely wrangle and control element 17, it became the completely invisible backbone of modern infrastructure.
Yeah. I mean, just look around whatever room you're sitting in right now. It is heavily produced to manufacture PVC, right? Polyvinyl chloride.
That's right. We add chlorine to the polymer chains of plastic to make PVC because that specific chlorine atom fundamentally changes the physical properties of the plastic itself.
What does it do to it?
It makes it highly durable, resistant to chemical breakdown, and crucially, fire resistant. That means the pipes inside your walls, the vinyl flooring under your feet, the window frames, and even the electrical insulation wrapped around the wires powering your devices, they all rely on chlorine.
And it isn't just heavy industry either. Our own biological infrastructure relies on it too. It is literally inside you.
Yeah, every single day, billions of people eat element 17 without a second thought. Because when you take that aggressively reactive chlorine and you allow it to satisfy its craving by stealing an electron from a sodium atom, you get sodium chloride.
Which is just common table salt.
Exactly. In that bonded form, the chlorine becomes this incredibly stable chloride ion. Earth's oceans are absolutely saturated with dissolved chloride, and your own blood requires those chloride ions just to maintain proper fluid balance across your cell membranes.
Wow, really?
Yeah, it ensures your nervous system can transmit electrical signals, and it facilitates muscle contractions.
Yeah.
Literally, without chloride ions, your body would just shut down.
So what does this all mean? It means there is this profound awe in realizing that both our own internal human biology and our massive external modern cities are running on the exact same chemical. It's holding our bodies together and it's holding our physical infrastructure together.
It is arguably the ultimate utility player in the universe's toolkit.
But we do have to talk about what happens when that fence we mentioned comes down. Because the very same intense reactivity that destroys pathogens and builds durable plastics can cause just absolute horror if it's unleashed on a human being in its pure concentrated gas form.
Yeah, we absolutely must look at the dark side of this duality. Breathing concentrated chlorine gas is devastating. And to understand why, we just have to go back to the mechanism. When you inhale the gas, it hits the moisture in your eyes, your nasal passages, your throat, and the really deep tissues of your lungs.
And it reacts with that water.
It reacts instantaneously. It forms hydrochloric acid and hypochlorous acid right there on the delicate, wet tissues of your respiratory system.
Oh my God.
You are essentially generating a highly corrosive acid inside your own lungs. It causes extreme cellular damage, rapid fluid buildup, and at high enough concentrations, it is fatal very quickly.
And humanity, having discovered this terrifying mechanism, basically chose to weaponize it.
The historical reality is incredibly stark.
Yeah.
In April 1915, during World War I, at the Second Battle of Ypres in Belgium, dense clouds of pure chlorine gas were deliberately released by forces across the enemy trenches.
Just unearthing the mugger and letting it loose.
Exactly. The wind carried this heavy, yellowish-green cloud over the lines, and because it's denser than air, it sank down into the trenches where the soldiers were taking cover.
It is horrific to even imagine. There was just no escaping it.
None. It caused absolute panic. It inflicted agonizing severe lung injuries, suffocating thousands of men. This marked the very first large-scale use of lethal chemical weapons in modern warfare.
It's just so grim.
It was. The devastation was so profound, and the suffering was so visibly catastrophic, that it eventually became a major catalyst for the international treaties we have today that restrict chemical warfare.
What's fascinating here is that it forces you to just pause and reflect. The exact same scientific discovery by Scheele and Davy, the isolation of element 17, it led directly to the elimination of cholera from global cities and directly to the horrors of Ypres.
The stakes just couldn't be higher with this element, which is exactly why modern industries treat chlorine with immense respect and caution today. Facilities employ advanced leak detection sensors, massive negative pressure ventilation systems, and extremely rigorous emergency protocols to ensure the gas stays safely contained within the industrial processes.
Which brings up a really practical question from the sources, actually. If pure chlorine gas is this incredibly dangerous, and we can't just safely mine it from a cave somewhere because it's always bonded to something else, how are we producing the tens of millions of tons needed to support all this modern infrastructure?
Right, it's a huge logistical hurdle. The secret lies in this really fascinating industrial technique known as the chlor-alkali process.
Okay, let's break that down. How does it work?
So you start with a very basic, super abundant raw material, which is just concentrated salt water, also known as brine. And you take this brine, put it into a massive specialized cell, and well, you pass a tremendously powerful electrical current straight through the salt water.
Wait, so we're essentially just electrocuting salt water. Like, how does electricity actually force a chemical separation there?
Right, so remember how we said chlorine is that molecular mugger?
Yeah, the one stealing the puzzle pieces?
Exactly. Well, in salt water, the chlorine has already mugged the sodium. They are locked together in this highly stable, incredibly tight chemical bond. To force them apart, you have to completely overpower that bond. The electrical current provides the immense energy required to literally tear the electrons away and force the chlorine to let go of the sodium.
Oh, I see. So electricity is basically the tool we use to meticulously tear the salt water apart into its most useful, highly reactive pieces.
It is a beautifully efficient molecular disassembly line, really. When you run this electrochemical process, you yield three incredibly valuable industrial products all at once. You get pure chlorine gas bubbling up, you get hydrogen gas, and the remaining solution becomes sodium hydroxide.
Which is used for what?
It's also known as caustic soda, which is another absolutely foundational chemical for global manufacturing.
It solves the supply problem so brilliantly. Like, we don't have to hunt for a deadly gas out in the wild. We just pull it out of harmless salt water right inside a carefully controlled factory.
Exactly. It provides the massive volumes of chlorine we desperately need, and it does so safely and reliably.
Let's just zoom out for a second and rapid fire some of the facts we've pulled from the sources, because honestly, the sheer scale of chlorine's presence on our planet is really difficult to wrap your head around.
It really is. Consider the oceans, for example.
Yep.
Chlorine exists in some form in every single ocean on Earth, primarily dissolved as chloride.
And it is fundamentally essential for life itself to function. Like you said, without it, your nervous system simply wouldn't fire.
And synthetically, we're producing tens of millions of tons of this element worldwide every single year, just to maintain the baseline operations of our society.
The sources make this incredibly compelling argument that few elements on the periodic table influence our daily lives as extensively or as invisibly as chlorine does.
If we connect this to the bigger picture, if we were to magically remove chlorine-based chemistry from the world tomorrow, modern civilization would effectively collapse.
Just instantly.
Pretty much. We would lose our sanitation systems, the vast majority of our durable plastics, countless life-saving pharmaceuticals, and just the fundamental manufacturing capabilities that define the 21st century.
It really does force you to reflect on the ultimate paradox of element 17. How can one single element be the lifesaver that protects billions of people from microscopic threats and the exact same weapon that causes such terror on a battlefield?
It brings us right back to our opening thought, and I think it is a crucial lens for understanding the universe as a whole. Science at its core is strictly neutral. Chemistry doesn't have an agenda. Element 17 doesn't possess a moral compass. The profound impact of chlorine, whether it is purifying a hospital's water supply or causing devastation in a trench, relies entirely on the choices humans make. We are the variable in the equation.
It's a heavy thought, but ultimately I think it's an empowering one. If we can learn to control the chaos, we can build the modern world. And that perfectly sets the stage for what comes next on our journey through the periodic table. Next time, we are moving on to element 18, argon.
Ah, argon. The invisible noble gas that absolutely refuses to react with almost anything?
It's the gas that quietly fills our light bulbs, protects industrial welders from the oxygen in the air, and hides some truly surprising secrets right inside the modern technology you're probably using to listen to this deep dive right now. You definitely won't want to miss it. So be sure to subscribe to Atomic 118 to join our ongoing journey as we uncover the incredible stories behind every single element in the universe.
And this raises an important question, one I'd really like you to think about as you go about your day. If an element as aggressive, volatile, and inherently dangerous as chlorine could eventually be tamed by human ingenuity to save billions of lives, what other seemingly dangerous forces in our universe are out there right now, just waiting for humanity to figure out how to harness them for good?